was comparing an even and odd function. So I was looking at this even function. For example, in this case, xt is the absolute value of t. If you sketch it, it will look like this. Okay, so if you look, if you choose a value at -2 or 2, it's going to give you the same value. When x equals to -2 and x is equals to x equal to 2, when time is, say in this case time or t exists, t is equals to -2 and t is equals to 2, that's going to give you the same value. That's an example of an even function. Another example I was trying to show you is the cosine. Cosine is also an even function. This is a cosine curve. If you look, for example, at -pi and -pi and pi, you get -1. Cosine pi is equals to cosine minus pi, and that's equals to -1. Same absolute values. I mean, same value, but different in sign. You get the same y value. You may call this x is xt. This is t. So you get the same xt value and plus minus pi. Similarly, like cosine minus pi over 4 is cosine pi over 4. That's going to be how much? Cosine 45 degrees. 0.707, is it?
0.707, sir.
Okay, thank you. So that's examples about even function. There now I was going to talk about some examples of odd function. So this is that goes through the origin. In this case, xt is just t. The absolute value makes it reflected like this. There's no absolute value, there's no reflection. For example, in this case, if you take, let's say this is 2, -2, x -2 is equals to minus x2. Right. When x is -2, the value Next is -2, the value is -2, right? When x is 2, the value is 2. Therefore, you have to add a minus here. In other words, x minus 2 is not equals to x2. Okay, so that's odd function. Any question?
No, sir.
Okay. So another example is another curve we might be looking at is the sine wave. Okay, the sine wave. For example, if you choose if you look here at this point and this point, sine is a maximum at pi over 2. It's 1. But on this side, at negative pi over 2, sine is -1. For sinus, sorry, it's not sinus, sine minus pi over 2 is not equals to or if you want to make them equal, then you must put sine minus pi over 2 is equals to minus sine then they becomes equal. You have to add a minus sign to make them equal. In that case, that's odd function. Any question?
No, sir.
Okay, now let's move to systems.
No, sir.
Okay, thank you. Systems. System. The system usually have an input xt and an output yt. or this is in continuous time domain. In discrete time domain, you can have an input xn. The output will be y as a function of n, discrete time. Or you can have a hybrid system. In a hybrid system, the input can be discrete time, the output can be continuous time, or the input can be continuous time, the output can be discrete time. Signals are processed inside here. Signal processing. Signals are processed inside the box. One example of a system, an example of a system is like, for example, you have okay, it's a small system here, and then you have a resistor inside here. System with just a resistor. Current go in, input is a current, okay, output is maybe a voltage, which is the resistance times the current. So that's a simple system there. Also an inductor maybe. An inductor. Input, current, output, inductance, multiplied by I di dt. So these are some examples of systems. Just one element systems. You guys are still around, connected? Hello?
Yeah,
Yes,
sir.
sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay, thank you. Okay, now we're going to study the important properties of systems. So please pay attention to this properties because you definitely will be tested in midterm. For linearity, or linear system. Let's say a signal coming in, call this x1t. Another signal coming in, call this x2t. Okay, there's another signals here. Maybe I have to draw this slightly bigger. Another signal, let's say sum of signal 1 and signal 2. Signal 1 input produce signal 1 y1 output y1t. Input, okay, input x2t, let's say produces an output that's called y2t. So the sum of inputs x1t and x2t produces y1t plus y2t. So to check for linearity, the two things you must confirm. One is the additivity. Additivity. This is the additivity of, okay. We should be able to signals. You should be able to add individual signal. That's one thing you must meet. The second criteria is that you must meet is homogeneity or scaling. Hello guys. Are you all still online?
Yes,
Yes,
sir.
sir. Yes, sir.
Homogeneity or scaling?
Yes, sir.
Okay, let's put it yeah, because there's a lot of space. So homogeneity and scaling. X1t produces Y1t. If you scale x1t by a, so you call this ax1t, then the output should reflect that by a. So this is called homogeneity or scaling. Now we combine additivity and homogeneity. So we have to combine additivity and homogeneity to get the superposition condition. So if a signal has to be, for a signal to be linear, it must meet the superposition condition. So to meet the superposition condition, basically, A1 x1t
Sir,
yes,
is it A is a constant?
beg pardon?
Is it A is a constant?
Yes, A is a constant.
Okay, sir.
A is not dependent on time. It's constant. Okay, so all these A's, A1, A2, all these are constants. So we combine additivity and homogeneity to meet the superposition principle or superposition condition. Then you should get the output also reflecting that. A1 y1t plus A2 y2t. Okay, so this meets both the additivity and homogeneity, and this is called the superposition principle. So if a signal can meet these two condition, then it's homogeneity. So we usually test for this part. We just test for this. Sometimes you can come and just test for this. You can just test for this part here. If it fails, then you don't have to move any further. If it fails one of these condition, let's say we fail additivity, then you don't have to go and prove homogeneity or scaling. So now we combine homogeneity and additivity to form the superposition condition. Any question?
No, sir.
No, sir.
Time invariant system. Time invariance. A test for time invariance. Let me draw this block diagram first. So the block diagram will illustrate how to test for time invariance. For example, you have an input coming in xt into a system. When it comes out of the system, it's called yt. Okay. And then let's say you delay this is already the output. Let's say this is the output. Now you're going to delay the output delay yt by t naught. If you delay the output yt by t naught, what you will get at the output is yt minus t naught. So this is the signal output obtained by delaying output yt by t naught. Okay, take a look at this and you tell me if you guys can understand this. xt coming in to a system, then the output of the system is yt. Now you put a delay on that output, and then to the final output is yt minus t naught. That is the output obtained by delaying the output yt. So this is called output delayed output. Okay. Okay. Can you guys follow this?
Yes, sir.
Okay, the next one. Okay, this one, okay, again, xt coming in into a system. Sorry, st, this is not, okay, coming in, xt coming in, and this is the input. Delay, now you're going to delay input or delay, just say xt, because we can write too much inside here. Delay xt by t naught. If we delay xt by t naught, the output is going to be, output from this block is going to be t minus t naught. And this is called delayed input. this delayed input now enters the system. The output that's coming from the system is called y dt. Okay, this output is due to the delayed input. Okay, this output ytd is due to the delayed input. But this output yt minus t naught is due to delayed output. Can you guys see the difference?
Yes, sir.
Define y dt. Okay, we're defining y dt. If y dt is equals to y t minus t naught if those two are equal, then the system is time invariant. That is the test for time invariance. We will look at an example in a while. Example, given output is equals to e to the x t. Is this time invariant? Very simple. All you have to do, now you have to do this first one, call this number one. Call this number two. So let's do number one first. So number one, what is number one doing? The number one is delaying the output. It's delaying the output by t naught, right? Delaying the output by t naught. That means you're replacing the t with t minus t naught. If you're replacing the t with the t minus t naught, then the t here also should be replaced with t minus t naught. Number two. Now number two is delaying the input by t naught. You delay the input by t naught. Where's the input? Here is the input. You just replace the t with t minus t naught. So therefore, you also have to replace this t with t minus t naught. Okay, this is called the y dt, right? Y dt. Because we already defined this output to be y delayed input. For delayed input, we have a subscript called yd as a function of t. Now let me ask you, now is y t d is equals to y t minus t naught? Are they equal?
Yes, sir.
Okay, look, just look here and tell me, are they equal?
Yes, sir.
What about the other guys? Are they equal? Are they? I think
Yes,
they went
sir.
for breakfast.
Yes, sir.
Yes, sir.
Yes, sir.
So therefore, it's time invariant. Yeah. Is this example clear?
Yes, sir.
Now let's look at another example that's not time invariant. Okay, now let's do this from one. In one, what do? You delay the output, right? So y t minus t naught, replace the t with the t minus t naught. If you do that, then you're going to replace all the t's with the t minus t naught. Okay, for that part, from 2, that's this block diagram here. For y dt, what we do, we just delay the input only by t naught, right? We just delay the input. We just replace the input t with t minus t naught. Xt is the input. Okay, now look at this. Look at this. Are they the same?
No, sir.
Therefore, not time invariant. So this is the test you should do to verify if something is time invariant. So once you know the principle, you can do that for any system and verify. I mean, here we are only doing simple system. If you want to do complex system, maybe you need to do some programming in MATLAB. Okay, can I move to the next one? Now let's do an example on linearity. Yes.
I don't get it in the y number 2, y dt equal to exponential minus t.
Y dt.
Uh,
Okay,
y
there,
is,
according to this block diagram here, y dt is the output due to the delayed input. This is the delayed input. Okay.
yeah, I know that is a delay input, but why we getting exponential power of minus t?
Minus t. Where?
Exponential minus t. Can you scroll down? Yeah. over there.
Exponent minus t. This one.
Yeah,
Yeah.
sir. Yeah.
Ah.
I don't get
Are
it.
you
Why?
asking?
Asking this. Yes, sir.
So you're asking why this is not changing?
Yes, sir.
Because we are only delaying the input. We are only delaying the input. Which one is the input here? The input is xt, right?
Oh,
The
okay, okay.
input is xt. Very good question, because a lot of people do not see this. So we already defined here from the block diagram, we are only delaying the xt, no other t's.
Okay,
We
sir.
are only delaying the t that's inside x, the parenthesis. But whereas on this case, for the case number 1, be delaying the output. When you delay the output by t naught, then there's a t here, then there's a t here, there's a t here, right? So everything changes. But in this case, we are only delaying the input. This is the input. So we are only delaying the input. This is not really the input. xt is the input.
Okay, sir. Got it. Thank you, sir.
No, this is really a good question. I'm sure most of the students there, they're just dozing off and they're not paying attention. I think you guys might have benefited from this question. Good question. All of you, please stay awake and ask question. Next time, you're going to be really, most people do very badly in this question, in the midterm. Most of them fail because of this. It may look easy, but you need to look in closer. Good question, JJ.
Okay, sir.
You guys should pay attention and ask question. If you don't ask question, what I'm going to do, I'm just going to upload a pre-recorded video. Then what's the point of doing live video if you don't ask question? I mean, you don't ask question for the sake of asking at random. You make sure you pay attention. You never know. So if you pay attention now, then later there's no confusion. Okay, let's move to linearity. Don't be ashamed to ask question. Don't be shy to ask question. There's a saying, if you don't ask question, if you ask question, then you are only stupid for once. If you don't ask question, you're going to be stupid for the rest of your life. After all, there's no such thing as stupidity. It's something that you are not clear. Every semester, I have to come back and learn this again because I forget myself. Any other questions?
No, sir.
Okay. Sometimes if something is linear or not, you can simply look at the drawing or the equation. It can tell, you don't really have to go through the mathematical proving. For example, yt is kxt. Maybe sometimes I should mention this is constant. So if you look at this, if you try to sketch this, and this is yt and xt. So if you look, this is going to be, it's like an amplifier with a constant gain k, right or not? So the input-output relationship is linear. You don't have to do any more mathematical proof. If you can just sketch it like this and show that this is linear. Any question?
No, sir.
Okay.
Excuse me, sir.
Yes, sir.
I don't understand about the sketch, but why the sketch is linear?
Why the scale? Why? Because you
Why
can see a linear. You can see. Can you see a straight line for the input-output relationship?
Yes, sir.
So whenever you see a straight line, it's linear.
Okay, sir. Understand, sir.
When there's an input-output relationship, it gives you a straight line, then the system is linear.
Okay, sir.
Graphically looking at it, if you want, you can prove it mathematically.
Okay, sir.
There's another, in English, there's another word for straight line is linear, right? I'm not sure, I'm just asking, let me Google it out and see. Linear, generally, linear means what? Linear in the English language. Linear, arranged or extending along a straight or linear, nearly straight line. That's the definition of linear. Arranged in or extending along a straight or nearly straight line. Non-linear. Let's say you have another example, yt is this linear?
No, sir.
Then you try to plot this. So this is yt is x squared t. So that's non-linear. I mean, generally, I'm telling you, like, this is graphically telling you, sometimes you cannot tell from the equation. Then you have to do the superposition testing. So, like for this example here, for the parabola, Now we can do the mathematical analysis to show that why this is not linear. This is a linear mathematical proof. For inputs, let's say this is the function, right? By t is equals to for inputs x1t, what will you get? If I replace this equation, see, this is same as xt squared, you know. So if I replace this with x1t, what do I get? What do I get? What do I get? If I replace the input with x1t, the output will be x1
x1 t minus t naught.
Where I got t naught? I'm just replacing, if this is the input-out relationship, yt is x squared t. So I'm replacing the xt with x1t. Replacing xt with x1t right here. Okay, that is going to be y1t. Now I put x2t. I'm just checking the additivity. I'm going to check additivity, whether it's adding properly or not. When I put x2t, that's going to give you x2 squared t, which is y2t. You guys follow so far? See what I'm trying to do? I'm trying to do this. I'm trying to do this part only now. For linearity, you need to check two parts, additivity and homogeneity. But sometimes you don't have to go and do all the tests. Just do one test enough. If it failed the test, you don't have to go and do the homogeneity. So I'm doing this right now. Do you guys follow? I'm trying to do this right now.
Yes.
Yes, sir.
Yes, sir. So therefore, if I replace the input with x1, okay, if you guys to match the box, I'm going to change this color so that you can see this red color. The red color refers to the box, first input. The second color is blue. The third one, x1t plus x2t. plug into the t plus x2t. Okay, square it. What do you get?
y1t plus y2t, sir.
Okay, I'm just going to put this in slightly smaller. This is just for reference only. Okay, let me put here so that you know what we are doing. So we're trying to okay. Go ahead and square it. This is for reference only. Put it on the side here. Maybe just leave it here. Or just leave it here now. I don't know where to put. Okay, from here, let's do it. X1t plus is you know how to FOIL, right? You guys know how to multiply this x1t. It's just like multiplying like x plus y squared. How do you do it? Into x plus y into x plus y. Remember? So do you know? This is, I don't know what you call, but in the US they call it FOIL. So you have to multiply them out. Once you multiply them out, what are you going to get?
x1 square t
X1.
square t
Say that again.
x1 square t
X1 square t.
plus 2x1 x2 t
Okay, plus, and then plus 2
and
x1
2 t x2 t.
plus 2 x1 t x2 t.
Yes, plus x2 square t.
X2 squared t.
Yes.
Okay. Very good. If you look at this, this is y1t. Maybe, okay, this is y1t. This is y2t. So we have additional garbage here, you see. To be able to maintain linearity, you should have x1t plus x2t should only give you so this is additivity. This is the additivity rule. We have it here. Can you see this, guys? It's additivity. This is your reference block diagram is telling you when you plus x1 and x2t, you should get y1t plus y2t. That is the additivity policy principle. But you know what you get here? You get some additional stuff. You're getting additional things here. So let me rewrite this. y1t plus y2t plus therefore the system is not linear. Okay, because we are getting additional things. According to the block diagram, you're supposed to get this. So since this already failed additivity, we have to know, we don't have to go any further and to test for homogeneity. Okay. Any question, guys? Are we still?
No, sir.
Any question?
No,
No,
sir.
sir.
Okay, thank you. Let me move on. We try to finish this properties today, so next week we can do some laboratory work online. So next, another property that you need to check is causality. All these funny terminologies. A system whose output depends on present and past inputs and not on future inputs. For example, a system is causal if the output at any time, note, any time, the output at any time this anytime, we just call this T naught. Anytime T naught is dependent on the input only for T is equals to T naught or less than T naught. That means the output should depend only on whatever you input, whatever time that you input, or the past inputs. So that, like, you know, like for in this case, what this means is T is T naught. Okay, this is, let's say it's a current input or input at any time, T naught. So for any time less than T naught, it's also T naught or all those inputs less than T naught. All those inputs that's less than T naught, for example, if it's T naught is 1, if T naught, for example, if T naught is 1, then the past inputs, all the past inputs are 0, -1, -2, -3. This is the input at any time. So these are all past inputs. If this is causal or not. I said that if I, let's say, if I put my input as 1, okay, let me put my input as 1. Then what is your yt is going to be? Let's say t was t naught, right? T is t naught, and then I'm saying that my t naught is 1. Just put a numerical number inside here and see what happens. So that is going to be 1 minus 2. So y1 y1 now we can see very clearly what's happening here. This is called any input. Any input, you know, 1. So what about this? This is the, sorry, this is the any out. I'm talking about the time here. I'm just talking about the time. Input any time. Input, sorry, output at any time. Sorry about that. Output at any time. Current time. Let's say currently the time is 1. The output at any time depends on past input. The output at any time depends on past input. So this is the timeline. You're standing here. So you input, you say, okay, t is 1. Input, then the output is at t is equal to 1. But that depends on the input when t is -1. So this is past, right? Past. So this is, according to our definition, what is a causal system? A system is causal if the output at any time t naught is dependent on the input only for t is less than t naught. So that means it can be past input also. Let me read this again. A system is causal if the output at any time t naught is dependent on the input only for t is t naught or less than t naught. So in this case, your T naught, T is less than 1. So is this causal?
Yes, sir.
Okay, this is causal. It is causal. Causal since the present output, in this case we call this one, the present output y1, that's a present output, is equal input of 2 seconds ago. Two seconds ago means past input. Are you guys okay? You follow this?
Okay.
Yes, sir.
But don't worry, we can always do more examples later. I already went through 2 past midterms, March 2018 and 19. You can look at those 2. Those videos are there. Also, we can always do that again. I plan to do more examples. Now let's look at another example here. A system xt is yt is xt plus 2. Is this causal? Let's check. Just put an input here. Call this, the output at t equals to 1 depends on what input. Put is 1 plus 2. So y1 is x3. This is future input. So this is not causal. Output depend on future input. Because output is already defined here. Okay. Future input. A system is only causal if it does not depend on future input. So since this is depending on future input, okay, let's say for example, this is your current input. This is your current input and then you're standing here. But then, sorry, this is the current output at 1. And then, but then your input is coming from here, 1, 2, 3. So, no, sorry, the other way. You're standing here 1. That is the output, present output at t equal to 1, but then your input is coming from future input. Okay. It's kind of difficult to explain sometimes, but the student can go through this and develop his own internal understanding. Only the student can help himself. The lecturer only can tell you a few things, but the student can get a deeper understanding by you have to go within yourself, and ask. There's a super intelligence within yourself. And then you have to go and consult with it and establish your own understanding. Any other questions?
No, sir.
Okay. So just a little bit more, keep calm, just a few more things. Okay, now stability. I don't want to give any formulas here, but just want you to graphically tell you what stability means. Stability. Definition: bounded input, bounded output. Something is stable bounded bounded input, bounded output, BIBO. For example, you have an input here. Call this a signal xt. Upper limit, lower limit, and then let's say you have a signal, but no matter how much this signal is varying, it's bounded input out. Okay, it's bounded by -1 +1. So this is an input bounded signal. If you put the signal, make this smaller, I made this too big. Then let's say this bounded input is going to create an output. Let's see what the output is going to look like. Say the output is bounded on the top is like 10 and the -10. The output is bounded by ±10. Output is yt. It also going all over the place, but it doesn't go above plus minus below above plus 10 or below minus 10. So the output is also bounded. So this is bounded input. Bounded output. I thought the graphical will be much helpful. If I write them in English, it will look like Greek to you. So can you see the concept? If the input for a bounded input, then if you produce a bounded output, then it's stable. Let's say if this is going like this, and then outside the it's not bounded anymore. Okay, it is keep growing somewhere and going like this. These are overshot like this. Then it's not bounded anymore because they don't have definite upper and lower bound.
So this is unstable, sir.
Now, right now, what you're seeing is it? This is stable. The earlier one that I drew was unstable.
Sir,
Yes, sir.
sir.
Yes, yes, sir.
For the red color, that definition is bounded output. Am I right? Not bounded input.
Yes, sir. Thank you very
Yeah.
much. Yeah, these are things. Please help me, because we're going to upload this, and then somebody might see it, and then they get more confused looking at our lectures. Eventually, I want to try to do a lot of problems, examples. Okay, now look at another example of bounded input, bounded input, bounded output. Okay, you have given a current, the output or a current, the output example. Okay, we are almost done, just a little bit more. Please bear with me, guys, so we can finish it. Even if we can finish it, just a little bit more. We'll come back next time. I don't want to rush in a hurry to finish it. We want to make sure that you guys understand. All these are very basic understanding important because sometimes you may walk into an interview and they will ask you very basic questions. You should be able to answer it. The output. Maybe I'll just do this. We have 20 more minutes. Maybe I'll just stop here in 5 minutes because you guys have been studying continuously for 2 hours, right? So it's not good. Okay. I'll just do one more problem and then we can call it quits. Then we can continue memory the next time. Just a little bit more. After that, we can jump into the lab. Okay, given an example, the output of a circuit let's say your output, current output, and this current output looks like it's a current through the inductor. It's going from minus infinity to positive infinity. Okay, V where B Vt is ideal source where is ideal source. And IT, if you integrate this, if you do your integration on this part, you'll get IT 1 over L. Since Vt is the ideal source, even without integrating, okay, if you integrate this, approximately what you will get is, this is a rough integration, you'll get V as a function of tau, okay? And then you multiply by this tau. Then you're going to evaluate from 0 to t. Roughly 1 over, so you can see you don't have to do anything. The output is dependent on a t. You can see the output is dependent on t. What is t? If t is a ramp function, ramp function means it will keep growing like this. Okay, so the input is not bounded. Sorry, the output is not bounded. If you try to sketch this IT versus VT, then you'll get something like a ramp. Just roughly, just look at the equation. If something depends on a t like this, then it's not going to be bounded. If the output okay, forget about these examples. Maybe I'll try to bring in more another example next time. This example is a little bit more. Okay, now I'll just complete this. Okay, if the output, if the input is Vt is ut, a step function. Okay, the input is bounded, the step function. Then what is going to be the output? Output is the current IT so this is the input. Input is a step function, 1 over L, but the output is going to be something like this. Input bounded, but output so as t goes to infinity, is 1 over L t. When t goes to infinity, of course, you know the t here is also, this is a constant, 1 over L is a constant, where t is not. Therefore, that's going to be infinity. The output is going to be infinity. That's showing it mathematically. Okay, the next time, do you guys have any question?
No, sir.
Okay, we'll continue the next time. Next time, just a few more things. Memory, bring in more tutorial, and then we also try to do